We are now going to talk about our section 5.6, which involves rational functions. We have 4 objectives for this section. A lot of it's going to be repetitive from before. It's just now we're dealing with it from a function perspective. And so once again, learning and practicing, finding domains, but now we're finding domains of rational functions. We're finding intercepts of rational functions. And then we're learning how to find asymptotes, really focusing more on the vertical asymptotes, but we'll mention the horizontal because horizontal will pop up when we look at our exponential and logarithmic functions. Uh, and um, and then horizontal asymptotes pops up a lot more once you guys get to calculus and you learn about limits. And then last but not least, we will practice graphing these rational functions. So definition, maybe I'll have a student read this in pink. Rational function. Yes, Arnella.
A rational function is a function of the form, is an R, I can.
Yeah, R of x.
R of x over P of x.
Over Q of x.
Oh, sorry, over Q of x.
So it's R of x equals P of x over Q of x. Yep, good.
So P of x and Q of x are polynomial functions, and
Q of x.
is equal to.
Beautiful. Yep, we don't want that Q of x to equal 0 because if it does, then we have a denominator of 0 and it's undefined. Great, thank you. And then what about domain in yellow? Yes, Zainab. Yeah, so exactly what we've been practicing for these past few days now. I like to just think about it as what are our restrictions? Denominator can't be 0. So what makes the denominator 0? And then anytime you're dealing with radicals that have that even index, so square root, quartic root, the 6th root, you need to make sure that underneath that root is greater than or equal to 0. Because if it's negative, then you bump into that imaginary world. Okay. This is just a slide stating the step-by-step procedure in finding domain, which you guys know already. So why don't we just jump into our first example where we're asked to find the domain of this function. So again, domain, what are those 2 restrictions? Denominator not equal to 0 and under radical is greater than or equal to 0. Lucky for us here, you don't see any radicals, so we don't have to worry about that second condition. But that first one, we do need to worry about because we have a fraction. And so x squared minus 9 cannot be equal to 0. Now that left-hand side is a difference of squares. We can factor that out into just x plus 3, x minus 3. Which tells us what are our 2 values that make this left-hand side equal to 0. Okay, what are those roots, those x-intercepts? Just negative and positive 3. So these 2 values are our restrictions. We can't have x be either of these because if we do, then our denominator is 0 and then it doesn't work. So how do we write this into interval notation? Again, if you're still a little confused, just draw a number line off to the side so that you can visually understand that we're excluding only those 2 numbers. So we're going to have open circles there, but everything else is free game. So we're going to shade everywhere else. We're going to have some unions, right? We're representing all numbers from negative infinity up to -3, soft bracket, because we're not including that -3. Then we're including all numbers between -3 and +3. And another soft bracket at that 3, because we're not including +3 either. But we are including all values that are greater than +3. So we need another union. And that's it. We have our domain. Okay. We have example 2. I don't know if this is a question or they just give you all of the answers. Yeah, this is just running through a bunch of different examples. So if we were to look at the rational function 2x² - 4 over x + 5, what's the domain here? It's literally all values of x except x is equal to -5 because that's what makes it undefined. And then in this second example, we have x² - 4. So our two restrictions are -2 and +2. In that third example, notice that we can't factor out x² + 1 in the denominator. And so there are no restrictions here. We have all real numbers for x³ divided by x² + 1. So that's a fun one. If we were talking about imaginary numbers, that would be a different story, because then you could factor it into x + I, x - I, but we're only honing in on the real number system. And then finally, we have that last example, our x² - 1 divided by x - 1. This is a fun one because if you did factor the numerator, you'll notice that the simplified version of the function, the x - 1's cancel out, but that doesn't mean all real numbers is your domain, because we are looking at this function as our original function. So we do need to mention, okay, if x is 1, we end up getting 0 over 0. But anytime there's 0 in the denominator, it's undefined regardless. So we need to exclude 0 from our set. Not 0, 1, which makes the denominator 0. Any questions on this one? And yeah, that's exactly what I mentioned. So that last example, again, right? We factor it out. It can be simplified to that x + 1, but we once again need to make sure that that 1 is still excluded because it makes it undefined. So our objective 2 is finding the intercepts of a rational function. Again, these are all just review. It's just now we're dealing with function notation. So how do you find x-intercepts? You set your y equal to 0, and then you either factor. If you're dealing with quadratic functions, you use your quadratic formula. If factoring isn't an option, you might need to use synthetic division if you're dealing with cubic or quartic or higher degree polynomials. And then y-intercepts are very straightforward. Wherever you see an x, plug in a 0, and then figure out what's left over. So why don't we give example 3 a shot where we're asked to find both our x and y intercepts. We'll start off with our y-intercepts just because it takes less than a minute to solve for your y, right? You just plug in 0 wherever you see an x. And so we end up getting -2 times 3 for your numerator. And then your denominator is -1 times 2 times -5. So that simplifies to -6 over +10, which is just -3/5 reduced. Which means as a coordinate, your y-intercept is just 0, -3/5. X-intercepts, what makes y equal to 0? So not what makes the function undefined, just what makes y equal to 0. So we're solely looking at the numerator here, right? The denominator is sort of what gives us those undefined values. The numerator is what makes the fraction 0. So x minus 2 we set equal to 0. Lucky for us, it's all factored out. And then x plus 3, we set that equal to 0, which means our two x-intercepts are going to be +2 and -3. So in coordinate form, we have, we'll put it in ascending order, -3, 0, and 2, 0. Yeah. Good question. So the 5 here is in the denominator. And so the denominator, we don't have to worry about when we're dealing with x-intercepts because this just makes it undefined. We look at the denominator of functions for finding domain. We set this equal to 0 to figure out, okay, what are our restrictions? But for intercepts, we just want our y. Definition of x-intercept is when y equals 0. Definition of y-intercept is when x equals 0. So if we set this equal to 0, we just want to look at our numerator. Yeah, no problem. Right, so now we're on to our asymptotes, which is our third objective for today. And we are pretty familiar with the arrow notation to represent, okay, as x approaches. We practiced a lot with this, especially when I taught you guys about end behaviors. As x approaches infinity, what happens to your y? As x approaches -infinity, what happens to your y? It's the same exact concept when we're looking at asymptotes. It's just with asymptotes, you're looking at it from it approaching from the left versus it approaching from the right. And that's where these little minuses and pluses come into play. So when you have a little minus, that's saying, okay, x is approaching a from the left. Whereas if you have a little plus in that exponent, that's saying x is approaching a from the right-hand side. And I'll show you guys in a moment on a graph more visually this taking place so that it really helps build that foundation for you. But all of the other ones, you're very familiar with because we've practiced these with our end behaviors already. Yeah. And so this example 4 is a very good representation of showing x approaching 0 from the left versus x approaching 0 from the right. Because when you're approaching 0 from the right-hand side, right, you're coming from that right, and what's happening? Whereas when you're approaching from the left-hand side, you're coming at x equals 0 from the left, and then what's happening? And so notice that in both cases, you are hitting that y-axis known as our vertical line x is equal to 0, which gives you, it's never going to hit x equals 0, but it's getting extremely, extremely close to it. It is approaching it, which tells us that x equals 0 represents a vertical asymptote for us. Any questions on this? Yeah, of course. So, this slide is really just helping you analyze the difference between this sort of negative exponent and this positive exponent attached to a number. And so that negative value stands for it's approaching from the left-hand side, and the positive is standing for it's approaching from the right. But the number itself is telling you, okay, what, because we have x, we're talking about all vertical lines here. And so that number is saying, okay, what's happening at this vertical line, x is equal to 0? Well, as the function is approaching from the left-hand side, okay, well, this is left, right? So as we take this function and we're going very close to 0 from the left, what's happening? Oh, we have this guy almost hitting x equals 0, but not quite. Well, what about from the right side? Okay, so this is the right-hand side. Now we're trying to hit this x equals 0 from the right. So we come in at the right and we have our pink. And so this is representing as x approaches 0 from the right, what's happening? Yeah. And then obviously when you have transformations involved, you'll be able to deal with different vertical asymptotes. Vertical asymptotes, instead of it just being at x equals 0, it could be at x equals 5 or x equals -20. And then we also want to take into account our end behaviors as well. But end behaviors, again, I think you guys have a good understanding of. As x goes to infinity, what's happening to our y? Our y is approaching 0. As x goes to negative infinity, our y is approaching 0. So what does that tell us? We actually have horizontal asymptotes too, right? Our function is never going to be hitting the origin. So we have a horizontal asymptote at y equals 0, whereas we have a vertical asymptote I'm going to do VA for vertical asymptote at x equals 0. So as our x approaches 0 from the right-hand side, what's happening? Our y value is shooting up to positive infinity. And then as we have our x approaching 0 from the right, our y is shooting down to negative infinity. They have that actually also represented here. Just wrote it slightly larger for you guys. So, again, this is just formalizing it, but what do we then have here, which I've said a few times now? We have what's known as our vertical asymptote at x is equal to 0. Asymptotes are never hit by the functions. They're only approached. They come very, very close. And so our formal definition of a vertical asymptote, if we have a function r of x, as x approaches some number c, the values r of x approaches either infinity or negative infinity. Then the line x equals c must be our vertical asymptote. And these are the just two different cases representing that. You can have a function where it approaches positive infinity on both sides, and we still have this vertical asymptote, or it can be opposite, where just like the example we saw previously, our 1 over x, where it approaches both positive infinity and negative infinity, but still yet never hits that vertical asymptote. Right. And then this is your locating vertical asymptotes theorem. I would say the biggest takeaway from this is you're essentially looking for the values that make your function undefined. And then once you have those values that are undefined, those represent your vertical asymptotes. So we'll be practicing that as well. Okay, so let's practice finding vertical asymptotes for these four functions here. How do we do it? We just figure out what are the values of x that make it undefined. So with f of x, we look at that denominator and we set it equal to 0, which means that x cannot be equal to 1, which means that is our vertical asymptote. Easy enough. Part B, can factor out that denominator into x plus 2, x minus 2, which means your two vertical asymptotes are x is equal to negative 2 and x equals positive 2. Part C, with h of x, we have x squared plus 1 can't be equal to 0. What do we notice about this one? Can we factor that left-hand side into real numbers, I should say? No, so no vertical asymptotes here, right? Our domain is all real numbers. We have no restrictions. And then finally, we have that last one, a trinomial in our denominator. So let's see if we can factor that. X plus 7, x minus 3, which means x can't be equal to -7 or 3. So what are our vertical asymptotes? X equals -7 and x equals 3. That's it. Questions? Yeah, Diego.
Yeah, for the B and D, if, I mean, there's gonna be a gap in the middle, right, where there's gonna be a approach.
Yep. Mm-hmm.
Size, how do I know which infinity is approaching? Like, two, you know what I mean?
You can test values between, you're saying, how do you know if it's gonna be approaching positive infinity in the y direction or positive infinity in the, or
Yeah,
negative infinity?
Yeah, it's reaching, like you said earlier, if it's reaching from the left, it's going to negative infinity.
Not all the time. It depends on the function. So, you can have a function where, let's look at b for instance. This is going to be, and maybe I'll put it on a different screen so you can really see it. I'm just completely making up this function. But let's say you have those two vertical asymptotes at both +2 and -2. So your function itself is never going to hit these points, but you are going to have a function visual between these 2 points. It's not like all of this doesn't matter. It still matters. But you can have a function that looks something like this. Go back to solid lines. So you have a horizontal asymptote here. You can have something like this. We're going to be learning a lot more about vertical asymptotes when we get into trigonometry, dealing with like your tangent functions specifically, but you can also have something like this. Now, how would you figure this out at this moment in your knowledge? You can just choose a bunch of different x values between -2 and 2, plug it into your function, and then plot out some of those points, and then you can connect the dots and figure it out. Yeah. Very good question. All right. Gonna continue. Any other questions or no? Okay. So now this jumps into the very brief overview of horizontal asymptotes. Horizontal asymptotes, to calculate them, I mean, honestly, I should just teach you how to calculate them because it's quite fun. When we come across an example, I'll show you how you can easily find it. But you learn more about that in calculus because you do deal with limits when you're calculating horizontal asymptotes. And so at this stage in your math career, you're going to be just exposed to functions that if you look at their end behaviors, you can easily calculate the horizontal asymptotes. That won't always be the case, but at this stage, yeah, it's quite straightforward. And again, what are horizontal asymptotes? They're just horizontal lines that are never hit by the function. So that's like the informal definition. And then our formal definition, as x approaches infinity or as x approaches negative infinity, your value of your function approaches some fixed number L, which represents, once again, that horizontal line. Down here are just some short visuals. You have a random function. It's getting very, very close to this horizontal line, but it's never hitting it. And then you have another function here, which is coming up from the bottom and approaches y equals L, but once again, never hits it. And so this is just a slide talking about how in this course, we're only studying how to graph rational functions in this general format, ax plus b divided by cx plus d. Once you get to calculus, you'll be able to graph more complicated rational functions. And that's kind of what I was saying before. You'll have a deeper understanding of calculating more horizontal asymptotes using methods that you learn in calculus. So let's do some more practice. We have example 6 here. 3x plus 7 divided by x plus 2. And now we want to sketch it. We want to label all of our intercepts and asymptotes on the graph. Okay. Sketching is always fun because you don't have to be super accurate with it. Just have to get the gist. Let's first identify our intercepts off to the side here. So we have our x-intercept and then our y-intercept. Y-intercept is, again, when x equals 0. So essentially, wherever you see an x, you just plug in 0 and calculate what your y is. This shoots to 0, this shoots to 0, so we end up with 7 over 2. As a coordinate point, 0, comma, 7 over 2. As a mixed fraction, 0, comma, 3.5. So now let's plot that. Okay. X-intercepts. We want to set this function equal to 0. So 0 is equal to 3x plus 7 over x plus 2. And specifically, what makes it 0, we're honing in on that numerator. So we just set 3x plus 7 equal to 0. Subtract 7 from both sides, and then divide both sides by 3. So we get our x-intercept is negative 7 over 3, which as a mixed fraction is about negative 2 1/3. asymptotes. Let's look at our vertical asymptote first. What makes the function undefined? That's simply when x is equal to 2, or sorry, -2. So our vertical asymptote is then x equals -2. Let's sketch that in. Right? Question? Oh, yeah, thank you. Right? And now let's look at our end behaviors. So as x is approaching -infinity, what's happening? And so if we plug in a really, really large number, I don't know, -1,000, what do we end up getting? We get -3,000 plus 7, still pretty close to -3,000. So I'm just going to put -3,000 for the numerator. And then we have -1,000 plus 2, which is very, very close to just -1,000, which ends up being +3. So what's happening here? As it's getting really, really, really large, our y value is it ever going to go below the x-axis? And y, I should say. And again, you're looking at it beyond that -2 point. So if you even plugged in -3 here, you would get -9 plus 7, which is -2, and then -3 plus 2, which is -1. So all the time, it's going to end up shooting out to be positive, right? So how do we sketch this out? It's going to be it's never going to go below slowly increasing, very slowly. That might even be too steep. And then we have this asymptote. We can, you know what we can do? We can all right. Now let's look at from the other side. And what do we have here? As x approaches positive infinity, so we'll put in 1,000 and we get 3,007 over 1,002, which is once again very close to 3, which is actually making me, we have a horizontal asymptote as well. Will it ever equal 3? Don't think so. Yeah, it's never going to be 3. So that's the way to determine your horizontal asymptote, right? Even if you chose 10,000 or 100 or 50, right? 3 times 50 plus 7, and then over 52, we get 157 over 52, which is very close to 3. I'll give you the exact. Divided by 52. Yeah, 3.019. Whereas when we were choosing values on this side, we were getting like 2.99. In both cases, from the left, as it approaches from the left, we hit that 3 value, or don't hit it, get really close to it. When we approach from the right, we hit that 3 as well, which means we need to edit this graph a little bit. And put in some horizontal asymptotes. Okay. So now what are we looking at? One graph there. And then our other graph is going to be, again, sketching it out. What do we know about this famous graph, right? This is very, very similar to our whole 1 over x. We're going to end up with this. And there we have it. We just have shifts that are taking place and some stretching. Any questions?
Where did you get the y asymptote?
The y equals 3? Yeah, so that was by utilizing end behaviors. So all right, you find your horizontal asymptote by looking at end behaviors. And so what we did, I know I computed it, maybe not the cleanest way off to the side here, but we looked at, okay, as our x is approaching negative infinity, what was happening? We were getting some value very, very, very close to 3. So as x approaches negative infinity, our f of x was approaching like 2.978. And then we chose even a closer value, and then 2.999, but never hitting 3. And how you can do that is, well, we did negative 3,000 or negative 1,000. And so negative 1,000 plus 7 times 3 is negative 3,000 plus 7 gives you negative 2,993. And then negative 1,000 plus 2 gives you negative 998. When you put that in 0.2993 divided by, you don't have to know the accuracy of this. I'm just showing it to you so you guys can see that it's really, really close to 3, but it's not going to ever hit 3. So we get this 2.998 as x is approaching infinity. And then as x is approaching positive infinity, what's happening? That's what we computed down here. We notice that f of x is, it really should, I'm doing this arrow as 2.998. It's just, it's approaching 3, right? Because when you compute it, you're now going to get a slightly higher value than 3. 3,007 divided by 1,002 gives you 3.0009. And then this one down here also gave you a very close value. 157 divided by 52 at 3.01. So you'll notice, okay, well then, as x is approaching positive infinity, we're getting closer and closer to that horizontal asymptote 3 as well. Does that make more sense? Yeah, cool. Any other questions on this? Yeah, end behaviors, use your end behaviors to identify your horizontal asymptotes, and then use undefined denominators to identify your vertical asymptotes. I will teach you a trick if you're getting really confused about the whole calculation from the left and right. If you look at your function, and this is what you learn in calculus, your variables, if they are of the same exponent, which they will be because that's the highest level that you'll ever get to, all you have to do is take your a divided by c, and that's your horizontal asymptote. So you have 3 divided by 1 equals horizontal asymptote. And then you're done. So that's the easy way to go about it. Works every time. Once you get to calculus, you'll be dealing with like 5x squared divided by 2x, and then you'll have different exponents, different degrees. And so in that case, you aren't going to have any horizontal asymptote there. But then if you have like x to the 3rd divided by x to the 5th, you are going to have an asymptote there, and it's not going to be coefficients. It's only the coefficients when your degrees are of the same. But again, that's the highest level that we're going to hit at this, not even point in the course, just in this course in general. So you're always going to just look at the coefficients and you're done.
So you don't need to do the other process.
It's good to know, but this really helps. It's good to know when you end up sketching out the entirety of the graph, but solely for identifying your vertical and horizontal asymptotes, yeah, just look at it this way. That way you can easily graph it in, and then it makes it easier to do your end behaviors. Yeah. Yeah.
And the y-intercept, how do you get negative 2 times 1/3?
Oh, good question. Definition of y-intercept, that's just one, x-intercept. You just look at the numerator and you set that equal to 0 because your definition of x-intercept is when y is equal to 0. So you set the whole function equal to 0, and then you hone in on that numerator part of the fraction, set that equal to 0, and then you solve for your x. Right? Subtract 7 from both sides, divide by 3, and you get -7/3. Now we're going to start with our next example, which is example 7. And here we are going to graph x minus 2 divided by x minus 3. Same exact concept, label all the intercepts, asymptotes, and then sketch. So let's do this one a little faster. Our x-intercepts, right? X minus 2, set that equal to 0. So then we get x is equal to 2. So as a coordinate, 2 comma 0. Y-intercept, when x equals 0, what do we get? -2 divided by -3, which is just positive 2/3. Vertical asymptote, we can't have the denominator be equal to 0, which means our vertical asymptote is at x equals 3. And then horizontal asymptote, look at the coefficient. Our horizontal asymptote is 1. Yeah, good. So now let's sketch this out. Plot some points. Let's do the asymptotes first. So y is equal to 1, and then x equals 3. Right, 2 comma 0, and then 0 comma 2/3. Might have to plot a few more points. Let's choose maybe some points greater than 3. So 5 and 6. We'll just create a little T-chart off to the side. When x is 5, when x is 6, maybe when x is 10. 5 minus 2 is 3, divided by 5 minus 3 is 2. 6 minus 2 is 4, divided by 6 minus 3 is 3. And then 10 minus 2 is 8, divided by 10 minus 3 is 7. So we get 5, 6, 7. The 10 we might not be able to plot. 3, 4, 5, 6. So 5 and 3/2, which is just 1.5. And then 6 is a little smaller. So now we could sketch this one. And then last but not least, don't forget to write your function. And that's it. Yeah, so the table, I'm just choosing random values just because our intercepts fell on this bottom part of our graph. And so this one was sort of like invisible. And so what I did was, oh, we have a vertical asymptote here. Let me choose some values greater than 3. I probably should have chose 4 as well, but I didn't. And we're sketching, we're not graphing, so it's like you don't have to be like 100% accurate with your lines. But what I did was I plugged in my X values and then I spit out what my Y values are so I could plot some of them so that I can create that little sketch.
So get your Y value, like 5 minus 2.
Yeah, you just plug it back into, because remember, this is Y is equal to your function. So you choose your X's and then you calculate it to spit out your Y's. So for 4, we plugged in 4. 4 minus 2 is 2. 4 minus 3 is 1. 2 divided by 1 is 2. So 4 comma 2 is a point on your graph.
So it's like you only change the X by the value that you choose.
Yep.
You just want a regular.
Exactly. Yeah. It's just being strategic, choosing good X values. Yeah. All right. And then that was the last example for this section, both, I believe. That was the last part of chapter 5.